Mm-hmm.
Okay, hello everyone, welcome to our group presentations, and our group is NestSense, and today we are going to present it by Techaphatr and Chachalit. Okay, so let's get started. NestSense, the smart home comfort and climate analytics systems. Okay, so before we go to the detail of our projects, I want to mention that have you ever met this problem? Okay, let's think that when you are outside of your house and you wonder that this your house is on fire, or your ice cream on your table is melting or something, or maybe your server is not cold enough. Yes, a lot of problem, right? Yeah, we also know that problem. So what if we have something that can do all of this to clarify of your wonder? We use a board, and then the board is observed for you. Right. And let's come to our project, NestSense. This project is going to fix that problem for you and also gonna observe most of the temperature, the humidities for your room. It's gonna be so good. Okay. Okay. So let's go to how does it work. Overall system of our website is have three main key feature. First one is the website. Second one is Kitbright, and the last one is API and database. Okay, so let's go through Kitbright first. Okay, so for Kitbright, we have a sensor for our project, which is a temperature sensor and light sensor. This is a built-in in Kitbright. And for DHT11 and HCSR 501 PIR is two of these is optional, and you can buy the sensors and plug to the Kitbright to use this feature. Okay. Okay. So firstly, when you open your Kitbright, you have to download the code of this code. Okay, into your Kitbright, and then you restart your board. And after you restart your board, your IDE shell gonna show the link, the IP of the website that you need to go config. Your task is to open your mobile phone, connect to Kitbright Wi-Fi, and then you put your home Wi-Fi and password in here. And after that, you click save. Then you're gonna get the UUID and the QR code. From the image, it's just the preview only. But if you already put in the form last page, you're gonna get the QR code. And after you get the QR code, then it's time for our website. Okay, so let's go to our website. Okay, for our website, firstly, you open our website, and then you're gonna see a beautiful landing page, and then you can click login or register, and then put in your account. Okay, and after you put in your account, you're gonna redirect into the dashboard. Then you click add, and you put the board informations, which is the area name, board tokens. Board token is the QR code that you get when you set up the board, or the UUID that is a text. You can also type it in here. And lastly, put your locations in the search bar, and then you pin it. And after you do that, boom, you're gonna get your dashboard ready, and you can see all of the board that you set up in real time. Okay, if it's offline, you're gonna see a gray icon. If it's online, you're gonna see a blue, a clean, orange, a red icon based on the data of it. Okay, so when you click on each icon, you can see the data on the right side. You can see the comfort score, you can see the temperature, humidity, light, and motion events in real time that Kitbright is get the data for you, and also the outdoor data, which is come from a TMD data. Okay, which also gonna filter it from the location that you pin in the maps. And you can also see a real-time graph, the difference between indoor and outdoor of temperature and humidities. Okay, now let's see on the workflows. Okay, so for KitBytes, for both set up the bot and also getting the data, we're gonna use KitBytes, send the data into the MQTT, and the Node-RED is going to handle that and query and update it into the database. Okay, and another main flow is the website, which is going to use a Next.js API or built-in endpoint in Next.js and query the data from the database. But there is one thing like a proxy thing that not related to two of this, but really help us to make the feature impossible. No, make the feature possible is the model training that we create a fast API, and then we're gonna do pulling the data from the database and then train the model to get the predictions of comfort score. Okay, and this is the database schema of our projects. You can see that there is a board, and then there is a sensor and also the outdoor that we map into the board using the ID of the board, and also we have a manual events, which we didn't use much of the manual events because it's the feature that you just click on the buttons and there's nothing to compare with, so we didn't go forward with that. And the user, which of course for our website. And since I already mentioned the database, so why not we go to our data of our website or our projects?
Okay, hello. I will talk about the data part. Okay, so what data did we collect? We collect more than 50,000 real sensor reading from 2 rooms, which is our primary data source, collecting over several weeks at 30-second intervals. And another data is our 308 outdoor weather snapshot from TMD API, which is our secondary data source stored in, and all of the is stored in my SQL via Node-RED pipeline. So how the data are collected? The kit byteboard read temperature, humidity, light, motion every 30 seconds and publish to MQTT broker, which put it to Node-RED and put into my SQL. And for the TMD API, we pull every 3 hours for outdoor condition. So here are the features we use for the model. It is temperature, humidity, light, motion, hours of day, and days of week. So here is a level distribution. So we have 3 comfort class with comfortable, moderate, and uncomfortable. So the class imbalance exists. We handle with SMOTE during training, and level originally is stored as the string in database mapped to integer before training. So exploring the raw data, we see that the temperature is the clearest temperature between classes, and humidity overlap more between moderate and uncomfortable. Light and motion are less discriminative on their own. Well, as you can see on the light, you can see that why it's stuck on the zero a lot because of my problem with the kit bright that I have a problem with the light sensor. So sorry about that. So here are the feature relationship. The temperature has the strongest link to comfort level. Temperature and humidity are moderately correlated, and the hours of day weekly correlate. Comfort varies through the day. So data preprocessing and adaptation. So we label the comfort moderate and uncomfortable to 0, 1, and 2, respectively. And feature extraction, we extract hour of day and days of week from the timestamp, and new handling, we drop low missing temperature and humidity, fill missing motion with 0. Class balancing, we using SMOTE via imbalance learn to balance the training set. Type conversion, we ensure all features are numeric before training. What drives comfort for the global variable? The temperature is the dominant predictor, about 65%, and humidity is on the second for 24%, about 24%, and time feature and context are less critical. Light and motion contribute the least. And different room have different drivers. So you see as the in the graph below, you can see that room D29, I'm gonna call this room 1. In the room 1, humidity is the top driver. This room is more humidity sensitive. And on my second room, the room F09, is the temperature is the top driver. The room temperature sensitive. That means the room is temperature sensitive, as you can see here on the graph. So when are the room uncomfortable? So as you can see from the data below, the table below, you can see that the room is uncomfortable, leading the uncomfortable leading peak at the midday hours from 10 to 15. Early morning and late evening tend to be the most comfortable and can be used to schedule cooling system automatically. Weekday versus weekend, the pattern consistent across weekday useful for planning automated comfort adjustment. But I gonna tell you one thing. I gonna tell you one thing is the data that we collect is a bit not not like the real world like normal day, because most of the time that we collect the data, we have the energy saving, so we kinda have more time spent on online learning, so we didn't leave our loop so much. So the data will be mostly comfortable, and it's also because of Songkran, you can see that on Saturday and Sunday, the room is have less comfortable rating more than other. Okay, here is the room by room comparison. The both rooms show distinct comfort profile, different in average temperature and humidity, suggest different ventilation and insulation. And room with higher percent uncomfortable need more attention. So, but this is not well because of the energy saving and the Songkran. So this will have to learn a bit more. Outdoor versus indoor. The indoor is on average 6.9 degrees Celsius cooler than outside. When the gap shrink, outdoor heat spike, so comfort become uncomfortable. Comfortable reading delta temp equal minus 9.6 degrees Celsius. It means uncomfortable reading is percent delta temperature about minus 1.7. Proof outdoor heat is direct driver of the indoor discomfort. So in summary, more than 50,000 readings from two rooms collected automatically. Temperature and humidity are the strongest comfort predictors. Each room have different dominant feature, and so per room model are better. Outdoor temperature directly drives indoor discomfort, and data was adapted. Level encoded feature engineer imbalance collected.
Okay, so now let's take a look on our overall website. So this is a look of a landing page, a dashboard, with scroll down of the dashboard, and yeah, this is our website. You can check it out in https://daq.tdktaco.dev or scan our QR code in here. So sorry about time taken for the presentations. Okay, so thank you so much for listening to our presentations.